Hello, and welcome to AMAT362, Probability for Statistics at UAlbany. This is Lecture 6. In Lecture 5, we introduced one of the most important notions in probability, which is that of conditional probability. We also introduced this notion of the law of total probability, which in its simplest form says that if I want to know the probability of an event A, what I can do is look at the probability of A given B weighted by the probability of B, and then consider the probability of A given B not occurring, B complement, times probability of B not occurring. In a more general form, it says something like this, that if B1 through Bn partitions omega, that's our total space of possibilities, our sample space, where each of these partition elements has some non-zero chance of occurring, then we also have that probability of A is equal to the sum from I equals 1 to n of the probability of A assuming BI occurs weighted by the probability that of BI occurring. This is why sometimes, and in fact, this term of law of total probability is the one used by this book by Bertsimus and Tsitsiklis, which I'll sometimes call the MIT book because it's one of the main MIT probability texts for undergrads. It should be contrasted with Pittman, who is one of our preferred texts in this class, who calls this the rule of average conditionals. So that is also called the rule of average conditionals by one of our textbook authors, Pittman. Of course, what is in a name? This rule by any other name would be just as sweet and just as useful. I don't really care what you want to call it, but just know that this is a way of computing probabilities. We saw this in some of our live lectures where we considered things like the Monty Hall problem, where we've gone through and we average over all the possible ways of a thing occurring, and then that gives us a way of computing the probability of an event. Today's lecture is going to firm up some of this understanding of conditional probability and focus on what I think is probably one of the most important lessons in all of probability or statistics, which is that of Bayes' rule. Which essentially tells you that the following is not true in general. Probability of A given B is usually not true, not equal to the probability of B given A. You can't just switch the order of conditionals when doing conditional probability. Really think about what each of these things means. In this setting, you're considering a world in which you assume that B has occurred. And that's not by any way, shape, or form the same as considering the world where A is assumed to occur. Again, these being some sort of abstract events. But a lot of people make this mistake, and it has a huge impact in some aspects of our daily life, including how do we judge guilt or innocence of people. So I want to take part of today to talk about two really serious examples, and also get at one of the concepts which is going to be central throughout this course, which is that of independence. This is sort of an assumption under which we can drop conditionals. Say the probability of A given B is the same thing as just the probability of A. So e.g. when probability of A given B is equal to just the probability of A. Knowing B doesn't affect anything about knowing A. Again, this is not true always. So let me go ahead and put a little caveat there. This is not true always. But when this is true, we have the extra assumption of independence at play. All right, so let's get down to it. I want to start by communicating something called the prosecutor's fallacy. And let's go ahead and state more fully what the prosecutor's fallacy says. So let's look at this. Prosecutor's fallacy. So let's imagine we have the following setup. We know a couple of things. We're in a, let's say, a city with 1 million people. When you take the whole capital district, you know, Albany, Schenectady, Troy, plus all these intermingling towns, like Latham and Colony, you get about 1 million people. And let's assuming that in this region, a horrible crime is committed. Luckily, there are some witnesses, and the police, in collaboration with the sketch artists and these witnesses, are able to piece together a sketch of the perpetrator of this crime. A sketch of the suspect is made. And let's assume that this is a sketch which is sort of good enough that only 1 out of 10,000 people fit this sketch. Out of 10,000 people. Fit the description. Let's say fit the sketch. They look like whoever is drawn in the sketch. So we're going to call this this right here, this event FTD, or they fit the description. So let's assume that, you know, the police are out and they see someone who fits the description and they arrest them. And now we bring this person into court, and they've gathered a jury of their peers, and the prosecutor says the following. He says, the probability of fitting this description is low. In fact, there's only a 1 out of 10,000 chance of a person fitting this description. And then goes on to say, it is thus unlikely that an innocent person would fit this description. Therefore, it is highly unlikely the defendant is innocent. Now, think about that. Does that reasoning seem convincing to you? So let's go ahead and say the prosecutor says, one, probability so it says of a, let's say, an arrested person, that the probability of fitting the description is low. And then 2 says it is unlikely that an innocent person fits the description. And then 3, consequently, therefore, it is unlikely the suspect or the defendant is innocent. So do we believe in this reasoning? Is this a good line of reasoning? Well, let's try to put some math symbols behind this so it can be really, really clear about what's being said here. And we can agree that, yes, the probability of fitting description is low. In fact, we're told it's a 1 out of 10,000 chance. But what is happening in question 2 or statement 2? It is unlikely that an innocent person fits the description. So let's go ahead and try to calculate exactly what that is, and let's use the language of conditional probability. So what is being said in step 2? So what they're saying is that the probability of fitting the description, assuming that a person is innocent, call this innocent I, is low. So let's see, how do we compute this? Well, remember, the definition of conditional probability is that I have to look at the probability of them both occurring and I divide by the probability of being innocent. So how do we compute this right here? What's the probability of fitting the description and being innocent? Well, we need to think about the size of our city, right? Or the size of our region. Here we've got 1 million people under consideration. And we say that 1 out of 10,000 fit the description. So I'm just going to say note. So 1 out of 10,000 times population of our city, 1 million, equals, well, 1 million is the same thing as 10 to the 6th, and 10,000 is the same thing as 10 to the 4th. So this is 10 squared, which is the same thing as 100 people fit the description. And so we're going to assume that the guilty person does fit the description. After all, it was crafted based on the observations of witnesses, and we're assuming that they're capable of crafting the sketch that actually captures the guilty person. But it also is sort of ambiguous enough that it catches 99 other people. So what that means here is that we have a 99 out of the total number of people chance of fitting the description and being innocent. The probability of just fitting the description period is 1 out of 10,000, which is 100 instead of 99 out of 10 to the 6th. So fit the description and innocent is a subset of fit the description. All right, and so then what's our probability of being innocent? Well, this is fairly large, right? There's only one guilty person. So there's 999,999 out of my 10 to the 6th. So this is the probability of being innocent down here. It's highly likely that most people are innocent. So if we do this math and we simplify, we get something like 99 out of 999,999, which is practically 1 out of 10 to the 4th. So almost the same thing as just the probability of fitting the description. Now the question is, and this is really what's happening in the sort of step from going from step 2 into step 3, is the following question. So here's a question. is it true that the probability of fitting the description, assuming you're not guilty, that's IC, complement of the person being innocent or being guilty, is this equal to, question mark, the probability, or 1 minus the probability of fitting the description and being innocent? You know, again, we thought about this like rule of complements. One way of computing the probability of something occurring, same thing as computing the probability of it not occurring, and then taking that number and subtracting it from 1. So it turns out that this is not true. So this is not true. Answer. No, this is not true. Why? Because after all, what's happening on the left-hand side, so over here, probability of fitting the description, assuming you're not innocent, is 1, right? Because we're assuming that the guilty person fits the description. And so, in particular, IC is contained inside of fit the description. So this is the same thing as probability of fitting the description and guilty divided by probability of guilty. Again, recognizing that the probability of guilty is just another way of writing not innocent. And so, since, just to use our sort of picture here, we've got our population of people, that's people, omega. We've got a group of people who fit the description. Oops, sorry. Fit the description. And there's 1 guilty person who fits the description, but there are also 99 people who fit the description who aren't guilty. Remember, if you just read this, fit the description and guilty, I'm taking the intersection of G and FTD, but that's the same thing as just saying that they're guilty. Probability of guilty, probability of guilty, which is 1. And we just computed that this number over here, probability fitting the description, assuming innocent, is small, but is not 0. So the left-hand side is 1, and the right-hand side is 1 minus 10 to the 4th. So in particular, this equation is not true. You need to be careful that you can condition on event, and then that determines a probability distribution. So what is true, let me just go ahead and say what is true. That the probability of A given B is equal to 1 minus probability of A complement B. Notice that the location of this little complement is not in the second factor, but rather it's in the first factor. So that's a subtlety which you need to make sure not to mistake. But anyway, so what should we be calculating when we're sort of thinking about this person who's on trial? You know, we want to know if they're actually innocent. So what's the probability? There's a question. What should we be calculating? Well, if you want to know the probability of being guilty, assuming they fit the description, this is the same thing as 1 minus the probability of being innocent, assuming they fit the description. What's the probability of being innocent, assuming you fit the description? Well, let's go ahead and figure that out. So here we have the probability of innocent, assuming you fit the description. Well, again, we have to compute what's the probability of being innocent and fitting the description. We need to divide by the probability of fitting the description. And we've already done the top one. There are 99 people who are innocent who fit the description out of a total population of 1 million. That's 10 to the 6. And there are 100 people out of my million population that fit the description. So canceling out the denominator, we end up getting that this is equal to 99 out of 100, which means in particular that the probability of guilt, assuming they fit the description, is only 1%. So essentially, you shouldn't lock people up just because they fit a description. You need to have some other harder evidence. Otherwise, anyone who fits the description, any of these 100 people, you would have thrown into jail, and only one person deserves to actually be in jail. So keep that in mind next time you're on a jury, that you're asking the right questions and computing the right probabilities, and also being careful about what is the dependence on your conditionals and which order are your conditionals in. So this all leads me to Bayes' rule, which is the correct way of switching order in conditionals. And there are 3 forms for Bayes' rule. All right, so let's go through the 3 forms of Bayes' rule. The simplest form looks something like this, which says that if you want to know the probability of B given A, then you can compute that using the probability of A given B weighted by the probability of B occurring, and then appropriately divided by the probability of A occurring. This is sort of the simplest form of Bayes' rule. So this is the simplest. But when we combine this with the law of total probability, or the law of averaged conditionals, we also have at least 2 other forms, which are worth noting. The third being the more general, and the second being a special case of it. But let's go off the special case of this. So 2, assuming probability of A, probability of B, and the probability of B complement is all greater than 0, then we can compute probability of B given A in terms of the top, probability of A given B times probability of B. But now I'm going to expand out this denominator to use this law of average conditionals, or the law of total probability. It looks like the probability of A given B times probability of B plus the probability of A given B not occurring times the probability of B not occurring. And then, of course, if we have a partition, so B1 through Bn, partition, the space of possibilities omega, then I can compute the updated probability of any one of these subsets in this partition occurring, so let's say the probability of BK given A is equal to the probability of A given BK times the probability of BK, all divided by this lovely sum over possible ways of A occurring when I've intersected with each of the BI. So this is probability of A given BI times the probability of BI. So these are sort of the three forms of Bayes' rule. Let's focus on the second case, because it leads to another one of these really famous examples of fallacious reasoning in common situations. So I just showed you one in the setting of the criminal justice system. Now let me show you one in the case of public health. So let's look at, say, the false positive problem. But maybe before I do that, let me go ahead and provide you with a little bit of language, which can be super useful when talking in this sort of setting. So I'm going to use B to introduce what I'll call some Bayesian language. All right, so at least in this rule, form 3 of Bayes' rule, we call the probability of BI occurring the prior probability. This is sort of our belief about something before we're given any extra information. Pause. Sorry about that. So continuing with this formulation of Bayes' rule, where we have partitioned our space into a bunch of events, BK, and we want to know the probability that I landed in that bucket, assuming that I observed the event A. This gives us a way of updating our prior beliefs about whether or not BK occurred. So continuing this dictionary, in addition to having this notion of probability BI being the prior probability of BI occurring before observing A, we then have the posterior probability where we assume we've seen A, and we can now update our belief of whether or not BI occurred. So this is the posterior probability of BI knowing A occurred. And so let's look at one of the most canonical examples of this, and where we want to update our prior beliefs to have some knowledge and after the fact or posterior to seeing that something's occurred. And this is a classic puzzle, and it's sometimes called the false positive puzzle or the false positive paradox. Again, it's not one of those real paradoxes. It's a fallacious paradox in the sense that it's counterintuitive rather than actually breaking some aspect of the laws of reality. Anyhow, so let's do it. So here we have the false positive All right, so many people tend to just do this example with made up numbers, but I want to do something that's actually maybe pertinent to people's lives. So let's look at a serious, but hopefully not too serious example that I just want everyone to be aware of. So as we all know, there is the very deadly HIV. So that's the human immunodeficiency virus. This is the thing that leads to AIDS, which is sort of an autoimmune disease that essentially destroys the ability of the body to fight off infections. And so someone who has HIV, where it has then led to AIDS, is then much more susceptible to infection from very common things, cold, et cetera, and thus are much more likely to die. Fortunately, nowadays, we have a lot more preventative and treatments for people who have HIV and how to control AIDS. But for a long period of time, especially in America during the 80s and 90s, like this was not the case. And it was really an epidemic. Anyhow, as of 2016, in New York State, the rate of people with HIV was something like 760 out of every 100,000 people had HIV. So let's go ahead and define this as an event. So this right here is a frequency, but we use these frequencies to determine probabilities. So let B1 be the probability that someone randomly selected from New York State has HIV. And let B2 be the event where you don't have HIV, so no HIV. So again, this frequency is exactly the probability of B1 occurring. So 760 out of 100,000, which is a little less than 1%. Because if it were 1,000 out of 100,000, then that's like 1 out of 100, which is 1%. All right, so probability of B2, it's a little over 99%. Set out explicitly, 99,240 people out of 100,000 don't have HIV. So for those of you who haven't done this, you should know that there is a process of actually getting tested for HIV, and people should be tested regularly. One of the problems is that you have to wait 3 months after possible exposure to really get an accurate reading of whether or not you have HIV or not. So this is sometimes called the third generation antigen test. And you have to wait 3 months after exposure to really know whether or not you have HIV or not. And for this particular test, the accuracy runs as follows. So the probability of a positive test, assuming that you actually have HIV, is 99.7%. So just to write that out, 997 out of 1,000 is one way. Alternatively, you could get a positive test and not have HIV. So that's the probability of a positive test given that you don't. And this is 1.5%. So again, notice that this is okay. These two numbers, so nota bene, probability of positive given B1 plus the probability of positive given B2 does not equal 100%. Because again, that's not the right place to have the complement. This is the same thing as saying, so because in general, the probability of A given B plus the probability of A given B complement does not need to equal 1. On the other hand, if we fix that second slot to be B, then we could say the probability of A given B plus probability of A complement given B is equal to 1. All right. So this right here is called the, this is sometimes called the false positive rate, which is still pretty low, but it's going to dramatically impact what we can conclude in the event that you take an HIV test and you actually get a positive result. Because this is the essence of Bayes' rule. So imagine you actually do test positive for HIV. What's the probability that you have HIV? And you're doing this here in New York State. So here's the big question. It's a big question. What is the probability of having HIV, which is the same thing as B1, given that you have a positive test? So think about it for a second. This test, we're told, is 99.7% accurate. What does that mean? Well, what that means actually is that assuming you have the disease, there's a 99% chance, 99.7% chance that you'll actually test positive for it. But notice this is not the same thing as this. And in fact, something like 80% of doctors, at least according to some study in 1999, would get this question wrong. Let's actually figure out what is the probability of actually having HIV, assuming you test positive. And the issue here is you have to throw in all of the false positives, which affect actually 99%, 99.2% of the population. All right, so let's compute it using Bayes' rule. So using Bayes' rule, says that this is equal to the probability of HIV. Let me just for the sake of keeping this compressed, probability of B1, assuming a positive test, is probability of a positive test, assuming you have HIV, times the probability of actually having HIV with no information, that's the prior probability, divided by the probability of a positive test. So that's really the thing we really need to compute here. We need to compute what's the probability of a positive test. So how do we do that? Well, we have to use the law of total probability. In order to compute this. So what is that? It says that the probability of a positive test is equal to the weighted average of the conditional probabilities, where I look at the space of ways in which you might test positive. So you could, for example, test positive and have HIV, which is given by this multiplication. This is the same thing as saying probability of HIV and testing positive, plus probability of a positive test, assuming you don't have HIV, times the probability of not having HIV. And if you work this out, you're going to get something like, well, what do we have here? So a 99.7% chance of testing positive, assuming you have it, but multiplied by only the 760 out of 100,000 chance of some randomly selected person in New York State having HIV, plus the probability of a false positive. Of course, we know the probability of false positive is small. It's only 1.5%. So written out slightly differently, it's 0.015. But this is multiplied by the much more likely situation, which is where you don't have HIV. Again, just taking 760 and subtracting that from 100,000 leads us to 992,000, sorry, or 99,240. And if you do this, just continuing this calculation over here, what we end up getting is something like 758 out of 760 HIV positive people will test positive. But something like 1,488 of the 99,240 people who are HIV negative will get a false positive. So again, what this all says is that if some random person takes an HIV test, probability of a positive test is about 2.24%. But we can still see that of this collective population of people who test positive, out of 100,000, so that looks like 1,400 plus 750 gives you roughly, looks like maybe 2,246. But still, almost 2/3 of that people are just HIV negative people who happen to test positive. So all this is to say that when you actually do the math and you get what's the probability of having HIV, assuming you have a positive test, is now the ratio of 757, let's call it 758, that's the people I had over here, out of this total population of 758 plus 2,246, yeah, something like that, which works out to roughly 33%. So all this is to say, if you test positive, don't panic. Still only 33% chance of having HIV. And so that's sort of the false positive paradox. It takes something which looks like it should be extremely accurate, but then when you look at the fact that you're testing for something that's very rare in a broader population, then that false positive rate ends up overwhelming the number of sort of true positives, which is exactly this number right here. Now, just for some context, I will say that testing has gotten better. So now they have what's called the 4th generation antigen test. I think it's more accurate earlier, so you don't need to wait 3 months, but still waiting closer to a month is necessary. Here, the probability of testing positive, assuming you have HIV, is something like 95%, but it saves its accuracy overall by using the fact that if you don't have HIV, so that's B2, the probability of testing positive is something like only 40 out of 10,000 people will test positive if they don't actually have HIV. And so in this setting, for this different test, probability of having HIV, assuming you test positive, actually works out to being something like 64.5%. Again, using the numbers I just gave for New York State as of 2016. So this is sort of a cautious example of how to invert probabilities. Let me just wrap up by concluding with one more bit of information, which is related to questions of when does conditional probability not matter? So we're going to get at the question of independence. Your little red, white, and blue here, but I won't bother with that. All right, maybe I will. Have some stars. All right, so what is independence? Well, we can say that two events, A and B, are independent if probability of A and B occurring is equal to the probability of A times the probability of B. Now, this has an alternative formulation where I can say, let's say the probability of A given B is equal to the probability of A. Or equivalently, by switching things around and assuming that the right things are non-zero, the probability of B given A is equal to the probability of B. So again, this independent being the defined word here. So let me just give you a situation which we already considered where one, we don't have independence, and two, where we do have independence. So here's two quick examples. So remember, we dealt two cards, let's say from a 52 card deck. And let's say E1 is the probability, or is the event that the first card is black. And let's say that E2 is the event where the second card is black. So are E1 and E2 independent? Here's a question. Are E1 and E2 independent? Take a moment to think for yourself. Phrased slightly differently, if knowing that E1 occurs, does that change the odds that E2 occurs? It does, because if you recall, these are not independent because we concluded that the probability of E2 occurring, assuming E1 occurs, well, again, we've dealt one card, that card we're assuming is black. So there are 25 remaining black cards out of a deck of 51. So 25 out of 51. But we know that the probability of E2, somewhat counterintuitively, was equal to 26 out of 52, which is 1/2, because you don't know what was the color of the card that was already dealt. And if you sum over the possibilities, you end up concluding that the probability of the second card being black without knowing anything else is still 1/2. And so the fact that these two numbers are not equal conclude that these are not independent. Now, the reason for this, said in slightly more generality, is that when we're dealing cards from a deck, we're often dealing with an issue where we're sampling without replacement. So Y without replacement usually leads to non-independent events. But on the other hand, imagine we're dealing with something like coin tosses, which we could equivalently think of as maybe a deck with 2 cards. Let's say 1 red, 1 black. Now imagine you're dealt 1, then you replace it and shuffle and deal again. So this is an example of sampling with replacement. In this case, the color of the first card and the second card would be independent. So if we define E1 and E2 as before, now we have that the probability of E1 given, the probability of E2 given E1 is still the same thing as the probability of E2, which in this case is still 1/2. Only 2 cards, red and black. There's equally likely that you'll get either the red or the black card each time. All right, so that's it for today. I apologize if the lecture went a little long, and I apologize for the interruption, but I look forward to seeing you all in class soon.